Good evening. Welcome back to this series of classes in quantum mechanics. Okay. Today we will try to discuss inner product, orthonormal basis, Hermitian operator, commutator and uncertainty. Right, the relation, essentially the relation between commutator and uncertainty. Okay. So we are trying to master the concepts, and these are some of the important concepts that we need to be very familiar with. So some of these things we discussed yesterday. We mentioned that complex number systems have, you can consider Z and Z star as dual to each other. Right? By dual we mean every Z has a unique Z star. These are complex numbers. Okay. And similarly, we can do it also for vector spaces. Right? Every vector has a corresponding dual vector. Okay. So corresponding to every vector space, there is a dual vector space. Corresponding to a Hilbert space, okay, corresponding to Hilbert space, there is a dual Hilbert space. Our aim is to introduce what we know, what we call as the inner product or scalar product. Okay. It's a rule in order to get inner product or scalar product. Right. What do we mean by a scalar product? It's a rule in order to get a number, a scalar from a vector, right, from a ket. Right. Okay. So just like complex numbers have dual version, there is also a dual version to vectors. You can imagine it as a complex conjugate vector space. Okay. So corresponding to every ket vector, there exists a bra vector denoted in this manner. All right. The angle is in the opposite direction. Bra vectors satisfy the same axioms as ket vectors. In other words, the bra vector also defines a vector space. So these are the points to remember in the case of bra vectors or dual vector space. So if A and B are the bras corresponding to A and B, okay, we call this as bra A. All right, this is how we call it. So if bra A and bra B are the bras corresponding to ket A and ket B, then this would be the bra corresponding to A plus B. All right. So there is a linearity in that sense. Okay. So if you have like a vector in this form A plus B, in order to get the corresponding bra, you just take the bra corresponding to each of the vectors. Okay. All right. And remember, to complex conjugate, an important rule, it's rather a postulate. Okay. If Z is a complex number and if you have a ket ZA, okay, usually we can also write it as ZA, doesn't matter. These are different notations which are allowed, right? The ket corresponding to it is, the bra corresponding to it is, you can write it as ZA, okay, but this you have to write it as Z star. Okay. So the bra corresponding to ZA is not Z bra A, it's not Z bra A, but it's Z star bra A. Okay. So you can write it as ZA inside a bra, but if you pull this Z outside, you will have to introduce a complex conjugate. Okay. So these are the notations that we will be using. This is an important rule. It's rather a postulate. Our aim is to introduce a scalar product. An example is this. We have got ket here, a ket A written as a column matrix. So when you go to the corresponding bra, what you have is, if this is a column matrix, this is a row matrix. Okay, this is a row matrix or a row vector, right? It's not just a transpose of this, but you also have to complex conjugate each of the entries. Okay. So this is the one-to-one correspondence that we have. These are the vectors and these are the corresponding bra vectors, all right, or the dual space vectors. Now we are ready to introduce inner product. Okay. So you can think of bra or the dual vector space or the dual vectors as a map from vector to scalar. Okay. So we have got some vectors. For example, in 3 dimensions, we have got some vectors. So how do you go from these vectors to scalars? Okay. So it's easier to relate it, or the analogy is easier to understand if you write it as a column vector. You usually write this. We take all the components in a specific basis and write it as a column vector. Now, how do you go from this to a scalar? How do you go from this to a scalar? You know that you have to multiply it with a row vector. Okay. So for example, if you have A, all right, so you need some B in order to go to go to the scalar, all right, in order to extract a scalar, all right, in order to get a scalar, okay, what you need is an object like this. Okay, for example, I'll write it as bx, by, bz. Now if you multiply ax, ay, az. Okay, so this is an object in the normal three-dimensional vector space, and this is an object in the dual space. Now if you multiply this, you know that you get a scalar quantity, bx ax plus by ay plus bz az. It's very much similar here, except that if you are in linear vector space, all right, you will have complex conjugates here, because these coefficients in general can be complex numbers. We said that in real vector space, these expansion coefficients are always real numbers. Once you go to linear vector space, which is a generalization, you will have, what do you say, the complex, the scalars involved are generally complex numbers. So you also need to introduce a complex conjugation. Okay, so the inner product, we will write it as a product of Bra and Ket. Okay, you don't have a nice way to you don't have a nice way of talking about a product of two vectors, but you can talk about a product of a Bra and a Ket in this form, right? You can talk about a product of a Bra and Ket in this form, and this is a scalar. This is a scalar. All right, it's important. There's one more way in which you can talk about a product of Bra and a Ket, but this is an operator. Okay, you can make a product like this. You can call this as an outer product, and this is an operator. Okay, this is an operator. We may be using it. The projection operator, for example, has this form. Okay. And in this manner, all right, in this manner, it is a scalar quantity. Okay. And the properties are this: if you have a vector a plus b, okay, and you need to take a product with the Bra vector C, Bra C, then this is how you do it. You just take the product of C with A and C with B, right? Bra C with Ket A and Bra C with Ket B. Right? And this product, there's no surprise, it's called a Bra-ket, right? A Bra-ket. So Dirac basically took a Bra-ket and split it into Bra and Ket. And the Bra-ket is a scalar, right? Scalar means it is a complex number. In our thing, it's generally a complex number. And there is an important property, or by definition there is this property to the scalar product. If you change the order, right, in which A and B appear, then you will have an extra complex conjugation. Okay, so you see that AB, the scalar product AB, is not equal to the scalar product of BA. Okay, instead it's equal to the scalar product BA star, the complex conjugate. Right, here we don't have that. Here we don't have that. Here we know that A vector dot B vector is equal to B vector dot A vector. All right, that's in real case, but these are complex numbers. All right, and it's also easy to show that if you take this combination, a scalar product of a vector with itself, then it is a real number. Okay, it's easy to prove. Okay, you can prove it. You can. So if you take A is equal to A star. All right, so you just substitute instead of B, you put A here. Right. So you see, you get this thing. So you see that something is equal to its own complex conjugate, which means that this is a real number. Okay. This scalar product, the fact that we construct the scalar product in such a way that scalar product of a vector or the inner product of a vector with itself is a real number, it's very important. All right. This is how we construct probabilities in quantum mechanics. Okay. All right. So now we are ready to discuss normalized and orthogonal vectors. Okay, so this is very easy. If the scalar product of a vector with itself is equal to 1, then we say that this vector is normalized. This is normalized. This is often used. All right, we use it in this form: psi with psi is equal to 1. Then we say that it is normalized. Okay. And if the scalar product is 0, then we say that it is orthogonal. Orthogonal. All right. So this is the generalization of orthogonality relation that we have in three-dimensional vector space. Over the orthogonal means at 90 degrees perpendicular. Right. Here that the meaning is not that they are orthogonal. Right. And it's an important point to remember that if a set of vectors are mutually orthogonal, okay, if a set of vectors are mutually orthogonal, which means that every vector in that set is orthogonal to every other vector, mutually orthogonal. Okay. Then they are also independent. They are also independent set. They also form an independent set. All right, the vectors are independent of each other. By independent, you mean that when you say the vectors in a set, okay, are independent, that means that you can look at the definition, but that basically means that if all these vectors are independent, you cannot express any of these vectors in terms of the other vectors. All right, you won't be able to express C in terms of A and B, B in terms of A and C, etc. Okay, that's what you mean by independent. So one way to obtain an independent set is to construct a mutually orthogonal set. The other way it's not true, which means that if you have a set of independent vectors, it need not be orthogonal. All right, they all need not be mutually orthogonal. But if they are mutually orthogonal, be assured that they will also be independent. Okay. And in the case of quantum mechanics, we need to construct what we call as the basis. We will always use orthogonal basis. We make sure that a set of vectors are independent by making sure that they are orthogonal, mutually orthogonal to each other. Okay. Now we can say what we mean by an orthonormal basis. All right, we have already seen this term in one of the problems that we discussed earlier. Okay. So what do we mean by the basis of a vector space? We already know what the basis means, but we'll make it a bit more rigorous. All right, so we say the set phi I, okay, the set phi I of maximum possible number of linearly independent vectors belonging to that space. So you have got a vector space, you choose the maximum possible number of linearly independent vectors and they form a basis. Right? They form a basis, and the number of basis vector would be the dimensionality of the space. Number of basis vectors, or number of number of all the independent vectors, or number of independent vectors is known as the number of basis vectors is known as the dimensionality of the space, or the dimension of the space. Okay. So if in a space you have got 3 independent vectors, we say that the space is 3-dimensional. Okay. If you have 4 independent vectors, we say that the space is 4-dimensional, etc. Okay. Now again, as I said, these are linearly independent vectors. In quantum mechanics, the basis is very important. All right, but almost in all cases, we make sure that the basis vectors are independent of each other by making sure that they are orthogonal. All right. So this is the easiest way to ensure that a set of vectors are independent. If they are orthogonal, they are automatically independent. So mutually orthogonal vectors are independent. All right. Dimension of vector space is the maximum number of mutually orthogonal vectors in that space. Okay. So you can say, you can define the dimension of vector space as the maximum number of mutually orthogonal vectors in that space. Right. So for example, in the 3-dimensional space, you can choose one direction, and you can choose one direction which is perpendicular to it. You can choose one more direction which is perpendicular to both these directions, right, which is mutually perpendicular to this direction. We usually call this as IJK or something, right, IJK. Okay. So we can choose one direction, we can choose one more direction perpendicular to that, orthogonal to that, we can choose one direction which is orthogonal to these two. Okay. Now you cannot construct a fourth vector which is orthogonal to all these 3. Okay. So that's why we say that the dimensionality is 3 for 3-dimensional Euclidean vectors. And in quantum mechanics, we almost exclusively use only an orthonormal basis, right, exclusively, because that's much simpler. Okay. So you don't have to use it per se, you don't have to always use an orthonormal basis, but we can always construct an orthonormal basis set, and it is much convenient. All right, things are much clearer in an orthonormal basis. Okay. So hereafter, unless otherwise specified, if you don't specify otherwise, if you are given a basis, we'll assume that the vectors are orthonormal. What do you mean by orthonormal? What do you mean by orthonormal? Okay, this is the defining property called orthonormality, which means that if these two vectors are the same, okay, if it's phi 1 with phi 1, they are normalized to 1. Okay, if the scalar product of a vector with itself is 1, and the scalar product of a vector with another vector, okay, the inner product of one vector with another vector is 0. Okay, if this condition is satisfied, we say that it is an orthonormal set. Okay, so this delta ij appearing here is known as the Kronecker delta. Kronecker delta, okay, and it has values like this, okay. This is equal to 0 if I is equal to, sorry, I is not equal to j, it's equal to 1 if I is equal to j, alright. So if you have got the same vector here, if it's phi I with phi I, then it is 1. If it is phi I with phi j and I is not equal to j, then it is 0, right. That's what we mean by an orthonormal basis. Okay. Now we'll come to the application of scalar products in quantum mechanics. All right. So we already said that the measurement probabilities, we already postulated how the measurement probabilities can be calculated theoretically. What did we say? If you want to measure an observable called represented by a cap, all right. Hereafter I may not distinguish between the word operator and observable, all right. We'll use it interchangeably. Okay, that saves us a lot of time, all right. So suppose you are measuring an observable a cap, okay, by which I mean that you are measuring an observable which is represented by an operator a cap, but I'll just say suppose you are measuring an observable a cap. We said that the result would be, we already said this, result is one of the eigenvalues of A, okay, the result is one of the eigenvalues of A. Right. Now, how do we find this? So, if you are measuring a cap on a state psi, right, what you do is that you expand this in terms of the eigenvectors of A. All right. These are the expansion coefficients, and okay, here I am using a very convenient notation. So, this is an eigenvector of A with eigenvalue AI. All right. So, here the notation goes like this. The vector is denoted using the eigenvalue inside the ket, okay. So in order to represent, by this I mean like this, if you have a cap acting on ai, okay, this means the eigenvalue is ai and the eigenvector is denoted by putting the eigenvalue inside the ket, okay. This is a very convenient notation, all right, okay. So in this case, now what's the probability that you will measure? What's the probability that you will measure, for example, A1 or A2, okay, an eigenvalue A2. We said that this is equal to modulus C2 square. Assume this is modulus C2 square. Okay. Assume that we are talking about normalized states, all right, which means that modulus square of all C1, C2, C3, etc. is equal to 1. All right, these are normalized. We don't have to always carry. If it's not normalized, you just do one step and normalize it. Then we have a normalized. What do you say? A normalized vector, all right, normalized state vector. Okay. So we said that P of A2 is equal to C2. All right. Okay. Now, how do you can also now represent this using a scalar product. Okay. Now, if you look at this, all right. Okay. Let me write it like this. If I write, okay, what I did is I wrote psi is equal to summation over I Ci Ai. Okay. This is what I wrote. All right. Now you try taking a scalar product with psi, all right, with the general vector aj, with the general eigenvector aj. So this becomes summation over I. This is a number, so you just write it like this, and what you get here is ajai. Am I right? Okay. Now we said that we'll always choose orthonormal basis vectors. So we'll see later that we'll see after in the next slide that for a Hermitian operator, the eigenvectors form an orthonormal set. All right. So if this is orthonormal, this means that this is equal to summation I Ci. If this is an orthonormal set, you can write it as delta ij. Okay, just like we said earlier. Okay. Now what does this mean? You are summing over I and you see that there is a delta ij here. Delta ij says that this is non-zero or is equal to 1 only for I equal to j. Alright, it's non-zero for only if I equal to j. For all other terms are 0, because if I is not equal to j, it's all 0. So only one term in this summation survives, that's when I equal to j. So this is simply Cj. Okay, you are summing over I, right, and it will survive only when I is equal to j, is equal to Cj. So what you see is that, what is Cj? Cj or modulus Cj square would give you the probability. So you can say that Cj is equal to aj psi. All right, this is known as the projection of the vector psi along a direction aj. All right, the projection of the vector psi along basis vector aj. Okay. So now you can write the probability of obtaining an eigenvalue A like this, right? So if you want to know the probability of obtaining a particular eigenvalue, what you do first is that you first project the given vector onto the eigenvector corresponding to that eigenvalue. Okay, so if you want to know the probability of measuring a particular eigenvalue. Okay, if you want to know the probability of measuring a particular eigenvalue, what you do is that you take the corresponding eigenvector. This is eigenvalue. You take the corresponding eigenvector. Let's say this eigenvalue is A. All right. You take the corresponding eigenvector and project the state onto it. Okay, project the given state onto the corresponding eigenvector and take the modulus square. This would give you the probability of measuring an eigenvalue A. I hope this is clear. Okay. Now this projection thing is not very difficult. We already know this from three-dimensional vector space, right? If you think of R vector, our favorite example, xi plus yj plus zk. Okay. What would you do if you want to extract this component x? Okay. What would you do is just take I dot R vector, right? This is the convenience of using an orthonormal basis. If you want to get x, you just take I dot R. In our notation, you are projecting the R vector onto the direction I, right? So if you have an R vector like that, this in three-dimensional vector space, this is the I direction. So if you project this vector along this direction, you will get this component x. Yeah? It's the same thing that you are doing here. Okay? If you want to find the probability, what you do is that probability of measuring an eigenvalue, what you do is that you take the given state and project it onto the eigenvector corresponding to the eigenvalue that you are talking about. All right, and you take the modulus square, you will get the probability measurement, the probability of measuring that particular eigenvalue. Okay, I hope that is amply clear. Right, so this is important. We will be using this in problems. Okay, sometimes we just need to find this projection. Okay, all right. So that's why we introduce the scalar products, and that's the reason why we are always using orthonormal basis. Look at the convenience. Okay, if it's not orthonormal, right, and these kinds of quantities we always need to calculate. Right, we always need these kinds of quantities. And if your basis set is not orthonormal, you just can't do this. All right, things get unnecessarily complicated. Okay. So even if your given set is not orthonormal, you can always construct an orthonormal set out of it. That's what we'll always do in quantum mechanics. Okay. Now, just like the orthonormality relation we had, phi I with phi j is equal to delta ij, another fundamental relation involving involving the basis vectors is known as the completeness relation. Right? It's known as the completeness relation. Okay. So by completeness, what do you mean by completeness? When you say that a set, when you say that the set phi I is complete, right? When you say the set phi I is complete, it means that, right? It means that any vector can be expanded, okay, in terms of this. Right? Only then we can say that this set is complete. All right. So which means that suppose the given state phi I, the set phi I is complete. That means that you take an arbitrary vector psi is equal to summation I ci phi I. You will always be able to do this. All right. But we already know that this ci or cj. Okay. If you need the jth expansion coefficient, what you have to do is that you take the jth eigenvector and just project the given state onto the jth eigenvector, right? In order to get this expansion coefficient, okay, corresponding to the jth basis vector, what you do is that you take the given vector and project it onto the jth basis vector. That's what we do here. Okay, so summation psi is equal to summation j cj phi j, which you can write it as cj is equal to projection. Right? There's a summation over here. I missed it. Right? There's a projection psi projected to phi j, that's Cj. All right. So the same thing we have written here. Now, if you look at this, we know that this is a scalar quantity. We know that this is a scalar quantity. Okay, and this is a vector, so there is no problem, we can just interchange them. So this we can write it as, okay, summation over j, summation over j, right? I keep phi j here and then bring this scalar here, okay, phi j psi. Okay, now what do we have? We have got psi is equal to something multiplied by psi itself, right? This means that whatever appears here is an identity operator. Okay, whatever thing that's appearing here is an identity operator. Okay? So sometimes we simply write it as 1. Sometimes we simply write this relation. This is known as the completeness relation. We simply write it as 1. Okay, but you must remember that it is generally a unit. It could generally be what do you say? If you are using vector algebra, for example, it's the identity operator. Okay. All right. This is known as the completeness relation. These kinds of quantities are very important. Okay? These kinds of quantities are very important. Why are they very important? Because okay, usually when we do physics, when we get stuck, we do one of these two things. All right. Suppose you get an equation, some equation, all right, or some expression, and you don't know what to do. Right. So what you do is, first thing you try is you add 0 in terms of something else, say x minus x or something, and then rearrange them. Okay. Another thing you do is multiply by 1. Multiply by. So in quantum mechanics theory, when you get stuck somewhere, you can always try multiplying by this quantity. Okay, you can always try multiplying by this quantity. Multiply by 1, it doesn't change, and then you will get some results. All right. For example, if you look, I'll just demonstrate this. Suppose you have got this operator a cap. This is some abstract operator living in the Hilbert space. We don't know what to do with it. Okay, we don't know what to do with it. All right. So we can, what do we do? We can write this a cap as, let's say you multiply on both sides with an identity. We can write it as I, A, I. No problem, because it doesn't change. All right. Now what do? You write this I in terms of a complete set of basis vectors. Okay. In terms of an orthonormal basis set. So this you can write as summation over I, phi I, phi I. All right. I have introduced just one I here. Okay. And you have got an a cap there. Okay. And then I introduced one more I here. Summation over j, phi j, phi j. Because this is identity, there is nothing wrong in doing this. Okay. Now the summation you can bring together here. Okay, so this you can write a cap as summation over I comma j. Okay, and what do we have here? Phi I. Okay, and you also notice that this combination is a scalar quantity. Right, this combination is a scalar quantity. This is a scalar. It's a scalar means you can just pull it around, no problem. Right, so I'll just first I'll pull this summation outside, and then I'll write this as phi I. I'll just write this first. I've got phi I, a, phi j, all right, and whatever is rest, whatever is left, phi I, phi j. Okay, all right. Now you see that you have expanded this abstract operator in terms of some of the basis vectors. All right. So these things, all right, these things are called the matrix elements of operator A between the basis vectors phi I and phi j. All right. This combination is a scalar quantity. It's a number. It's a complex number. Generally, we say that this is the matrix elements of operator A between phi I and phi j. Okay. So this means that you can decompose an operator. You can decompose an operator into matrices. Okay. These are elements of a matrix. It has two indices, and these are elements of a matrix. This means that you can represent operators by matrices. All right. You can represent operators by matrices. Okay. This you can think of some sort of basis square matrices. Okay. This quantity is some sort of a basis square matrix. All right. I hope that's clear. This is how we can represent an operator by matrix. All right. And the matrix will change. The elements of the matrix will change depending on the basis you choose. Okay, you could choose the basis, you could choose the eigenvectors of the Hamiltonian operator, you could choose the eigenvectors of the momentum operator, and depending on this, the matrix elements will change, all right, but they all represent the same matrix. All right. And also I want you to understand that these quantities, all right, quantities like this, these are perfectly allowed. Okay, this multiplication is also allowed, and you will see that this is an n by n square matrix, okay, in some notation. All right. So if you, for example, if you take a quantity like this a, b, c, okay, corresponding to this, and then you do a star, b star, c star, okay, this multiplication is allowed, and you will get a 3 by 3 matrix. Okay, so this multiplication is actually allowed. Okay, it's known as an outer product. Okay, so we discussed completeness relation. It's interesting, we said. Okay, and now we'll discuss what's called as a Hermitian conjugation. Okay, these are the basic concepts I want you to keep in mind. Okay. So first we'll think of complex conjugation. Right? First we'll think of complex conjugation. Okay. And Hermitian conjugation you can think of as a generalization or the corresponding thing we do for matrices or operators. Okay. So complex conjugation. Suppose you have, as I said, suppose you have a ket given by AZ, or let's say a ket given by ZA. Okay, what's the corresponding bra? Corresponding bra would be, it's not equal to AZ, right? It's not equal to AZ, but it's equal to AZ star. Right, it's equal to AZ star. Right. Similarly, suppose you have an operator acting on a vector. Right. Suppose you have an operator acting on a vector like this. Okay. What's the corresponding? We know that if an operator acts on a ket, you get another ket. Right. But what's the corresponding bra for this ket? This is a ket. We know that this is a ket vector. Okay, because an operator acting on a state changes the state. You get another ket. Okay. If this is a column matrix and this is a square matrix, you get another column matrix by this multiplication. Okay. All right. So if you have a vector given by m cap a, what's the corresponding bra? It's not ma. It's not ma. I'll write it here. Okay. The corresponding bra is not am. The corresponding bra is not am. It is, you need some notion like this. All right. Corresponding to complex conjugation of this complex number, you need something here that we call as a dagger. All right. Now I'll make this more concrete by giving you a more general definition of what do you say, Hermitian conjugate. All right. This dagger thing is known as a Hermitian conjugate. All right. So this is the change you need to make to an operator. Okay. When you change from a ket to a bra. Right. You know what you need to do to a complex number when you go from a ket to a bra. Okay. Correspondingly, you have to do something to an operator when you go from a ket to the corresponding bra. Okay, and that something that you do is known as a Hermitian conjugation. Hermitian conjugation. Okay, but we'll need to make it a bit more concrete or a bit more general. So we won't leave this side open. All right, we won't leave this side open. We'll put some state here, because generally when you are talking about operators, they always have to be acting on something. All right, you cannot just leave them alone. Okay, not always. Sometimes you can, but not always. All right. Now, here I am saying that if alpha, this combination, all right, you have got alpha z beta is equal to beta. We know that if you have alpha beta, okay, we know that this is beta alpha star. Okay, this was by definition, this is how we defined our inner product. Okay, all right. So, what if you have a complex number in between, alpha z beta? Okay, what if you have a complex number in between? All right, then what's the corresponding? If you just invert it, what's the corresponding thing? We'll write it as beta z prime alpha star. All right, so we'll do the same thing. And what's this z prime? We can show that this z prime is equal to z star. All right, how do we show that? For example, this alpha z. Okay, I think I should write it somewhere here. Okay, I'm just motivating the definition, all right, so that it's easy to remember when you do problems. Okay, all right. So if you have got alpha z beta, all right, this also can be written as alpha z beta, all right, alpha z beta. Okay. Now we know that this is equal to, by the definition of scalar product, we know that this is equal to Z beta alpha star. Okay, Z beta alpha star. Right? Is that correct? Okay. But now this Z is inside a bra. Here it was inside a ket, it's inside a bra now. Now if you want to take it out, this is equal to, or this is equal to, if you want to just pull it out, you will have to write it as beta Z star alpha star. Alright. So this is how we introduce this. This is one way to introduce the Hermitian conjugation. Right? If you have, instead of this complex number, an operator, it makes more sense. Alright. So that's the same thing that we do here. If alpha a beta is equal to beta a dagger alpha, we don't know what this a dagger is, but we need corresponding operator. If you have an a here, we need a corresponding operator in such a way that this relation is satisfied. Alright. Then this a dagger, whatever it is, we call it as the Hermitian conjugate. Hermitian conjugate of A. Right? Just in the way that we call Z star as the complex conjugate of Z in this relation, if this relation is satisfied, you need to find the operator. Okay? You need to find the right operator or the changed operator in such a way that this relation is satisfied. Right? And that operator is known as a Hermitian conjugate of operator A. Okay? And in the case of matrix, it's really simple. If these are matrices, you know that. I won't go into the details, but it's easy to show that this A dagger is equal to, okay, A star transpose. If this is a matrix, okay, if you want to get the corresponding dagger, okay, what you need to do is that, okay, corresponding Hermitian conjugate, you need to complex conjugate all the elements of the matrix. If this is a square matrix, all right, the dagger, taking dagger means you complex conjugate all the elements of this matrix and also take the transpose. Okay, that will give you the Hermitian conjugate of a square matrix. Alright. I think you already are familiar with these things, but if we are dealing with differential operators, alright, if you are dealing with differential operators, you need to be careful in order to show that something is Hermitian conjugate or Hermitian adjoint, it's called. Okay, so you need to calculate it using this relation, alright, because the right side of a differential operator cannot be left blank. Okay, alright. Now, okay, now corresponding to a real number, there is something in the operator thing, it's called as a Hermitian operator. Right? What do you mean by a real number? A number Z is real if Z is equal to Z star. Am I right? Right? Yeah, a number is real if it's equal to its own complex conjugate. In the same way, an operator is called a Hermitian operator if it is its own Hermitian conjugate. All right? And operator A is Hermitian if it's equal to A dagger. If A is equal to A dagger, then we say that it is Hermitian. Okay, and if you are dealing with differential operators, you will have to use it in this manner. All right, if alpha z beta is equal to beta z alpha star without any star here, then we know that z is equal to z star. In the same way, all right, we said that alpha a beta is equal to, generally equal to beta a dagger alpha star. Okay, but if this is equal to, instead if this is equal to beta a alpha itself, then we say that if this relation is satisfied, okay, there is a star there, if this relation is satisfied, we say that A is a Hermitian operator. A is a Hermitian operator. Okay, so this is a lot of mathematical things that we need to learn. We need to get familiar with in order to really start calculating using quantum mechanics. Okay. All right. Now, once we know what Hermitian operator is, all right, once we know what Hermitian operators mean, okay, we come to what sometimes is referred to as the fundamental theorem in quantum mechanics. All right, perhaps the most important theorem when we do quantum mechanics. Okay. All right. So we have already noticed that if this operators are Hermitian, these Hermitian operators have a very important place in quantum mechanics. All right. If Hermitian operators have real eigenvalues, we have already seen that the eigenvalues of a Hermitian operator are always real. Okay, and we saw that for this reason we choose Hermitian operators in order to represent observables. Okay. We always choose. Okay, we choose only Hermitian operators to represent observables in quantum mechanics. Okay. And what follows? Right, the theorem that follows serves as a foundation of quantum mechanics. It's easy to prove this theorem, all right? I won't prove it here, but you have to remember that this is one of the most fundamental theorems of quantum mechanics, all right? It is this: the eigenvectors of a Hermitian operator form a complete set of mutually orthonormal basis sets, mutually orthonormal basis vectors, all right? This is the reason why quantum mechanics works. Without this, we couldn't have made this mathematical formalism, right? Fundamental to this mathematical formalism that we are talking about, the way we calculate probabilities, the way we calculate expectation values, all right? Fundamental to this is this theorem, all right? The theorem that the eigenvectors of a Hermitian operator form a complete set of mutually orthonormal basis vectors. Okay, if this weren't true, we couldn't do what we were doing. Okay? So this means that any vector in the space can be expanded as a sum of the eigenvectors of a Hermitian operator. Okay, so if you want to, as I explained earlier, if you want to know the probability of measuring a particular probabilities associated with measurement of particular operator A, okay, particular observable A. Okay. What you do is that you take the state psi and expand it in terms of the eigenvectors, because the eigenvectors form a complete set. Otherwise, we wouldn't be able to do this. And this, if it has to be an observable, it has to be a Hermitian operator. And if it's a Hermitian operator, the Hermitian operator eigenvectors, the eigenvectors of the Hermitian operator will form a mutually orthonormal set. So you can write this as summation over Ci Ai. Okay. This fact is crucial to the way we introduce probabilities. Now you say that the probability of measuring a particular eigenvalue Ai is modulus Ci square. Okay, this is how we do it. Okay, and we can also show that eigenvectors corresponding to distinct eigenvalues are orthogonal. That's the reason why we can make the set orthonormal. Alright. Now this is the case if there is no degeneracy, and even if there is degeneracy. What do you mean by degeneracy? If there are more than one vector, alright, if there are more than one eigenvector corresponding to one eigenvalue, okay, if there are more than one eigenvector corresponding to a given eigenvalue, we say that there is a degeneracy, alright. So the space is degenerate, we say. Then we can actually choose an orthogonal set from that, alright. It's known as is the process that we use for this is known as Schmidt orthogonalization. You might be familiar with this from your mathematical physics class, or we will be studying more detail. It's not very difficult, all right. You just, from a given set of vectors, you just choose a set of mutually orthonormal vectors, and this process, right, a nice process for this is known as Schmidt orthogonalization. Okay. All right, since it's so important, I'll say that in summary, the eigenvectors of a Hermitian operator form an orthonormal basis. This is very good because we need orthonormal. We always use orthonormal basis in quantum mechanics, and you don't have to look far for this orthonormal basis. You just take some Hermitian operator, take their eigenvectors, and you can expand any vector in the terms of these eigenvectors. Okay. All right. Now again, it's all a bit too much to take in, perhaps for some of you. Right? Let's look at a simple problem, just to relax a little bit. Right? Now consider two kets. Okay, the kets can be written like this. Right? What do we mean when you write these kets like this? Okay, what does it mean when you write the kets like this? It means that this psi, all right, can be expanded in some basis. Okay, let's say the basis is phi I. Let's say the basis set is phi I. Right. So we can write it as summation I Ci phi I. Okay. Write it here. Okay. So you can write a given set in terms of some basis set summation I Ci phi I, where this is the basis, and these are the expansion coefficients. Okay. Now once the basis is set, you don't have to worry about the basis again. You can just write down this expansion coefficients as a column matrix. Okay. That's what this psi means. These are the coefficients of expansion in a particular basis, or this phi I, this components of psi I, these components of psi are the expansion coefficients in some given basis. Okay. We always do this, as I said earlier. A vector is equal to axi plus ayj plus azk. All right. We don't have to worry about the basis. Often we will write this as a column matrix. right? But once you change the basis, once you change this basis, these numbers also will change, right? It's the same state, you can represent it in different bases, right? The state you can represent in terms of the eigenvectors of the Hamiltonian, the eigenvectors of the momentum operator or position operator, whatever you like, right? And this expansion coefficients, you can write it in a column matrix and you can represent the whole vector by it. Okay? So we have got two vectors here. Okay? So they are asking to find psi star and bra psi. All right, psi star would be just taking the complex conjugate of all these elements, all right, and that would be, so I'll just write it here, psi star, okay, would be simply minus phi I, 2 and plus I, okay, but whereas ket, the bra psi would be simply minus 5I, okay, you have to take the complex conjugate, you also have to take the transpose, 2 comma I. Okay, so you shouldn't confuse between taking the complex conjugate, even though it's known as a complex conjugate of a vector, all right. You shouldn't confuse between taking the complex conjugate and taking the bra. By simply taking the complex conjugate, you don't get the corresponding bra, or you also have to get a transpose. Now the question is psi normalized? If not, normalize it. Okay, is the state normalized? That's the question. So how do you find if the state is normalized? You check whether the inner product is equal to 1. If it's not 1, you have to make it to 1. All right. Okay, so how do we calculate this psi, the inner product? So this we already did. Okay, this we already did. Okay, now we calculate the norm of psi. All right, the inner product of a vector with itself is also called as the norm. It's also called as the norm of the vector. Okay. Now we calculate this, you just take this, we already calculated the corresponding bra and the bra corresponding to psi, you just combine them, that means you multiply this and you get the number 30, which means that it's not equal to 1, it's equal to 30, right. Now how do you normalize this vector now? You divide each of the component, by square root of 30. Okay, you divide each of the component by square root of 30. So here also you will have divided by square root of 30. Okay. Now this vector is normalized because if you take the scalar product, you will get an extra. Okay, if you get an extra 30 on the denominator, and that 30 will cancel this 30 and you will get 1. Okay, this is what we mean by normalizing. This is what we mean by normalizing. All right. So this is what the psi is not normalized. By multiplying each of the components by 1 by square root of 30, it becomes normalized. All right. So chi is the normalized vector that we constructed from psi, in such a way that this is equal to 1. All right. Now the question is whether psi and phi are orthogonal, right? And these kinds of questions have been asked in competitive exams. See, it's really easy to solve that question if you know what to do, right? What do you, if you want to know whether these vectors are orthogonal, you just take the product, okay? Psi, phi, or you can take phi, psi, right? You can take any of this. Okay? And if it's equal to 0, then you know that it is they are orthogonal, right? And one of the questions that was asked once for a net exam was they gave one of the numbers as a, right? One of the components as a, and they asked the following questions: what is a? What is a if, okay, if psi and phi are orthogonal? All right. So the information given is that two vectors are orthogonal, and you are asked to find this one of the components of it, one of the elements of the one of the components of the vector. Okay. So you just construct the scalar product, equate it to 0, and you will know the value of this particular number. Okay, that's how you do it. And this question was asked in one of the net exams. Right. It's a very easy problem. Right. They just gave the components, and instead of 2 here, they gave an a. Right, and they said that it's orthogonal to another state given by phi, then what's the value of a? It's really easy to calculate it if you know what to do. Right. So such conceptual basic questions are being asked in competitive exams. Okay. Now let's go into expectation value. Right, now let's work with what do you say, normalized vectors. This means that this is normalized. Okay. Now let's work with normalized vectors, which means with that psi is equal to 1. All right. Now in that case, we say that this is the expectation value of an operator A. All right. But yesterday in the previous class I gave you another expression for the expectation value of operator A. What was that? Okay, what was that? I said that the expectation value means the average value. Alright, so I said that the expectation value of A can be written as modulus of C1 square, okay, multiplied by the corresponding eigenvalue plus modulus of C2 square multiplied by the corresponding eigenvalue plus modulus of C3 square multiplied by the corresponding eigenvalue plus etc. I said this is the way to calculate the expectation value because this gives the probability of measuring a value A1. Right? So you multiply, you just multiply with the probability and add, you will get the expectation value. This is what I proved in the last class. Alright, you can check the video if you are not familiar with this. Okay? Now I am saying that it can also be calculated in this form. Right? So how do we do that? So in order to see that, an easy way to see is that you again expand psi in terms of the eigenvectors of operator A. So you write it as summation over I, okay, Ci Ai, okay, right. The corresponding bra would be psi is equal to summation over j. You don't use the same index for summation. Cj star Aj. All right. Now you just put it in here. Let's check if what I said is correct. All right. What I said yesterday is actually correct. So if you put it in here, just substitute it all in here. You see that this is equal to summation over j comma I. I'll put it all together. All right. I'll put it all together. So that is summation over j comma I, and you will have a Cj star Aj, okay, and operator A multiplied by, here you will have Ci Ai. Right, I pulled the summation out here. So this is equal to summation over j comma I, okay, Cj star. This is just a number. Let's bring it here. Cj star Ci, right, Aj Ai, right. But what were this Aj and Ai? We said that these were eigenvectors of this operator. So what we did is that we expanded the psi in terms of the eigenvectors. Right. So I'll write it here. Once we expand the state in terms of the eigenvectors of this operator, what we get is summation over j comma I. I'm just writing it down from there. Cj star Ci Aj A cap Ai. All right. All right. Now you use the fact that this is an eigenvector, so you will get an eigenvalue, a real number, Cj star Ci. Okay, you pull this real number outside. We use the fact that A cap Ai is equal to Ai because we are denoting the eigenvectors by the eigenvalue. So the eigenvalue is Ai. Right, so that Ai you can pull outside, and what you have is Ajai. Okay. Now we use the fact that the eigenvectors of the Hermitian operator form an orthonormal set, which means that this is delta Ji, our Kronecker delta. Yeah, this is delta Ji. So if this is delta Ji, you just carry out the summation over j or I. All right. One of the summation, and you will see that the only term that survives is j equal to I. So one summation is gone, and you can write a summation over I, because the only summation that will survive is for j equal to I. So you lose one summation and you put j equal to I. This is Ci star Ci, okay, and what you have is Ai, okay, that's equal to, okay, and finally I will write it here. So that's equal to summation over I modulus Ci square Ai, right. That's exactly what I have written here, right. That's exactly what I gave yesterday. This expectation value of A is equal to modulus of C1 square A1, modulus of C2 square A2, modulus of C3 square A3, etc. Okay. Or in shorthand notation, we said that we can write this as summation over I modulus of Ci square Ai. Okay. So it's exactly the same thing. We get exactly the same thing. Right. So this is one way to calculate the expectation values. So if the state is given, you need to calculate the expectation value of an operator, which means the average value of an operator. Given the state, this is what you will do. This is what you will actually do. Okay. All right. Now, if the state is not normalized, of course, you have to normalize it by dividing it by psi, that's all, right? The norm of the vector. So, this is the general definition of calculating the expectation value. I hope that is clear. All right, now let me come to this point, right? Measurement operators and a common misconception. Now, there is a very common misconception about what this measurement means and what these operators are, etc. Okay? The serious problem is that even certain textbooks, even certain serious textbooks, makes this mistake. All right? For example, if you take the textbook by Zetteli, okay? If you take this textbook on quantum mechanics by Zetteli, which is otherwise a good book, especially for preparing especially for preparations in competitive examination, it has a large number of problems, many of them solved. Okay, so this is a very good book to prepare. Okay, to prepare for competitive examinations. Okay, but if you look at the postulates of quantum mechanics as given in this textbook, you will see that they have made a very serious mistake, and I want you to know that such mistakes or such misconception exists. Okay. Now, what did we say earlier? Right? I'll just summarize again. A measurement of an observable always causes the system to jump into an eigenstate of the dynamical variable that is being measured. Right? So, if you are making a measurement on the state psi of the observable A, right? After the measurement, what you get is that you get an eigenstate of operator A. This is what happens after measurement, right? So, the measurement actually changes the state. Measurement actually changes the state, right? This is the state before measurement, and when you measurement, what happens? It jumps or reduces into an eigenstate of the observable that you are actually measuring. Right? So, if you are measuring energy of a system, all right, what happens? The state changes into an energy eigenstate. If you are changing the moment, if you are measuring the momentum, the state changes into a momentum eigenstate. If you are measuring the position, the state changes into a position eigenvector. All right, this is what happens. Okay. And operators, these are appearing in mathematics. All right, these are appearing in mathematics. This we just use to calculate eigenvalues and eigenvectors. All right, we use operators to calculate eigenvalues and eigenvectors. Okay. A common misconception is this: measuring an observable is the same as operating with the corresponding operator on the state. Okay. This is a misconception. Okay. Because of the name operator. All right. So, measurement is not operating on the state. All right. So, the textbook, for example, Zetteli, I don't remember exactly what he says, but he implies this thing. He says that the measured, if you are measuring A cap, or if you are measuring A cap on the state psi, he is saying that the measured state, or the misconception is that the state changes into A psi because A is operating on psi. This is not true. All right. If you are measuring A on psi, all right, the state does not change to A psi. All right, this is not the state after measurement. All right, if you are measuring A on the state psi, A psi is not the state after measurement. You have to keep this in mind. Okay? It's a very common misconception because this terms operators, it's operating on the state, it's changing into another state. That's all true. Right? But it's happening on vectors. All right? It's happening in the mathematical space. If you take a vector, act upon it by an operator, it changes into another vector, but that doesn't correspond to a change during the measurement. It's entirely a different thing. All right. So, I will repeat it. Suppose you want to measure the observable A on a state psi, it is not correct. Okay, it's not correct to say that the measurement of A changes the state to A psi. This is wrong. All right, this is completely wrong. So, if Zetteli says that on measurement, right, on measurement psi changes to A psi. Okay, or Zetteli, I am not quite sure if Zetteli exactly says it like this, but he has made this mistake. If you check the postulates part in the textbook by Zetteli, you will see that he has made this mistake. All right, he has given this misconception even in a serious textbook. Okay, this you have to be careful against. Okay, he says that psi goes to A psi after measurement. If you measure A, this is not correct. It's wrong. All right, it's true that psi goes to one of the eigenstates of A. All right. Now we come to another important concept called commutator. Again, very important. I am giving you only the important things. All right. So the operators have a very important property that their commutators are not equal to 0. Okay. All right. So the commutator of A with B is written as AB minus BA. All right. You take it in different orders, in different order, and find the difference between them. This is known as a commutator. Okay. Now, if these are two numbers, all right, if you multiply two numbers in different orders and take the difference, you'll get 0. But operators are not numbers; they are special objects, and generally, A with B, the commutator of A with B, is not equal to 0. Okay. This is important. This is very important. All right. So one of the reasons for some of the weirdness comes because of this. All right. Especially uncertainty. We'll see how uncertainty comes from this. All right. And there's another important result. If A with B is equal to 0, if the commutator of A with B is equal to 0, then eigenvector of A is also an eigenvector of B. Okay. This hat should have appeared here. I'm sorry. Okay. All right. So if the commutator of A with B is equal to 0, then eigenvector of A is also an eigenvector of B. Okay. This is for the non-degenerate case. We don't discuss degeneracy. This is very easy to prove. All right. So for example, if AB is equal to 0, okay, then AB is equal to PA. Right. If we use this relation here. Right. So now if you are acting it upon by an eigenvector of A, okay, A, this is an eigenvector of operator, this is equal to BA, right? But we already said that this is an eigenvector of operator A. So we see that, okay, from here we see that ABA is equal to A multiplied by BA. Okay, this is the eigenvalue and this is the eigenvector corresponding to this eigenvalue. Right? So now what do we see? Okay, we see that B acting on A is some other vector, all right, is also an eigenvector of operator A, right? Because we can write this BA as some other state alpha. Okay, so you see that A cap alpha is equal to A multiplied by alpha. Right? So we already said there is no degeneracy. You see that this changed vector alpha is also an eigenvector of A with the same eigenvalue, right? Which means that this alpha should exactly be the same as A, except maybe for a constant, right? Because otherwise it would become another vector. But we already said there is no degeneracy. Corresponding to eigenvalue A, there is only one eigenvector, all right? So A and alpha cannot be eigenvectors of A, operator A, all right? Vector ket A and ket alpha cannot be the eigenvectors of operator A corresponding to the same eigenvalue small a. All right. This means that this alpha at most will be different. Right. At most the change in alpha would be by a constant. Okay. A multiplied. So let's write this constant as Okay. But what was this alpha? Alpha was B acting on A. Okay. Right. So you see that this eigenvector of A is also an eigenvector of B, because operator B acting on it gives just a constant multiplied by the same state. Okay. It's easy to prove this. Okay, you can check. The important thing is that if the commutator is 0, then eigenvector of A is also an eigenvector of B. Alright. And important thing is that if this is not equal to 0, then an eigenvector of A will not be equal to the eigenvector of B. Now we come to uncertainty. I will just conclude with uncertainty. Okay. So we have just seen that if you have non-commuting observables, which means if B is not equal to 0, okay, then they can have no common eigenvectors. There is no common eigenvector. Right. So the eigenvector of A, I will write it as a set like this. Eigenvector of B, I will write it as a set like this. Alright. So the eigenvector of A is not an eigenvector of B if they do not commute. This means that this AI can be written because both these form basis. Both these are basis. Okay, basis vectors. So you can take one vector from here and expand it in terms of eigenvectors of B, because this is also basis. All right. CK, BK, something like that. All right, as we have written here. All right. Now what happens? This means that the states with definite values for operator A, right? What are the states with definite values of operator A? These are the eigenstates of operator A, are not state with definite values of operator B. This is why we have uncertainty, all right? So if two operators are not commuting, all right? So the eigenstate of operator A, if two operators, for example, x and p, all right, these are not commuting, then an eigenvector of x is not an eigenvector of p if they are not commuting. And what's an eigenvector of x? Eigenvector of x means it's a state with a definite value for x, all right? If you are in an eigenvector of x or position operator and you are measuring the position of it, you will get a definite value, right, so to speak, right? It will be in a range, etc., but let's not go into subtleties, okay? So x with p is not equal to 0, then eigenvector of x is not eigenvector of p. Okay, so when you measure the position, it goes to an eigenvector of x, right? But it doesn't have a definite value of momentum, right? This is the reason. This is the fundamental reason for uncertainty. All right, this is the fundamental reason for uncertainty. In other words, uncertainty, I can say that uncertainty is like this. Okay, uncertainty principle comes from this fact. Okay, uncertainty principle comes from this fact. It is this fact: there is no common eigenvector to non-commuting operators. Okay, this is the reason for uncertainty. This means that if there is common eigenvector, this means that there is no state, all right? There is no physical state with a definite value of position and definite value of momentum. Okay? So there is another misconception regarding uncertainty. It is this: people think that it's because we make a measurement and something changes, all right? It's because the disturbance caused by the measurement. But uncertainty is not, the quantum mechanical uncertainty is not due to some measurement you make. It's not because you disturb the system. Okay, it's simply because there is no such state with a definite value of x and p, all right, or which there is no state with a definite value for a and b if they do not commute. Okay, in other words, by state there is no electron, for example. Okay, if you are talking about electron with definite position and momentum, because we already said in our formulation that if the mathematical framework is correct, we said that corresponding to every electron we will have a vector in Hilbert space, right? And corresponding to every vector we will have an electron, right? So there is no such electron, there is no such vector with a definite position and definite momentum, all right? And in other words, the reason why we cannot measure the position and momentum of an electron simultaneously is because such an electron does not exist. Okay, there is no such electron existing with a definite value of position and a definite value of momentum. Okay, now this is the reason why we can actually show that the generalized uncertainty relation can be written in terms of the commutator. Okay, if the commutator is 0, then there is no uncertainty. If the commutator is not 0, then there is a non-zero uncertainty product. This uncertainty in A and this uncertainty in B. By this uncertainty, we mean square root of square of the expectation value minus expectation value of the square minus square of the expectation value. Right? This is the definition for uncertainty, and the product of uncertainties. Right? The product of uncertainties is non-zero if the operators do not commute. Okay? That's the reason for the celebrated Heisenberg's uncertainty principle. Okay? Now with that, I would like to conclude today's class. I hope you enjoyed the lecture. If you have any doubts, please join the Google Meet link given in the description. Okay? Thank you.